Hey guys, it's been a while since I've recorded, but I'm going to be doing the Year 12 Apps Finance Test of 2020 this time. Okay, it's going to be all calc, so I have my TI Inspire calculator at the go down the bottom here. Alright, but before we actually get into the test, I figure it's worthwhile quickly going over some of the things that we're going to look at and refer to throughout the test. So, we have simple interest or flat rate interest, and your it's gone fuzzy. Let me just fix that. That should work. Cool. Where your interest is equal to your principal times your rate times your time. IPRT. Okay. And the thing about this formula is you got to make sure that your units for the rate and the time must match. So if you've got your percentage per annum, time needs to be in years. If you've got a percentage per month, then you need to be timesing by the number of months. Okay, if the rate does not match the time, then you're going to have an issue. All right, and then a continuation of your simple interest is that your final account balance, which we usually refer to as A, is equal to your interest plus your principal. Okay, simple interest is an arithmetic sequence. All right. Now, as a recurrence relationship, which you'd normally recognize in case you've forgotten from your sequences, it needs to be made up of, in terms of Tn, not n, okay, Tn. So your next term, which we've got Tn plus 1, is equal to your previous one plus some sort of flat rate difference here. It's linear. Simple interest is linear. Okay, so you're just adding or sometimes subtracting. Okay, and you've got your initial term here on the side. You've got to do both parts for your recurrence relationship. This first term is always forgotten. I'll put another reminder on the next page. All right, D is the change per period. So how much interest you've been charged would be a good step there. All right. Just a quick side note, because it comes up pretty regularly, is that how n is defined changes things, and this comes up a lot in the finance section, is that sometimes n is defined as the beginning of the beginning of the nth month or nth year or something like that. And so you'd get this situation. So we have our years, we have the beginning of that year, we have the interest that changes in that year. We've just done flat rate because that's what we're on, and then the value at the end of that year. So if it is phrased as the beginning of the nth year, you got to be careful, because at the beginning, when you write T1, what you're actually saying is the beginning of the first year. Okay, nth year, first year. So at the beginning of the first year, it is $10,000. Okay, this can cause some issues because we want to sometimes write T0. T0 is really only used when you have the end of the nth year. Okay, if we had T1 in this situation, this is the end of the first year, nth year, first year. Okay, whereas T0 comes into play here because it's the beginning. Nothing has happened. The beginning of the 0th year doesn't quite make sense, but no time has passed here. Okay, the end of 0 years means the beginning of the loan and at 10,000. So if you see end of the nth year, T0 is acceptable. Beginning of the nth year, T0 would not work. Not really. Okay, but yeah, just make sure that you're paying attention to the definition of n, and you should be fine. Okay, don't forget that interest can be thought of as the amount charged to borrow. Okay, so on top of your principal is how much your interest is. Kind of comes from this idea. Anyways, that's simple interest, which we do a little of. Really, we want to be talking about compound interest. Okay, this is your compound interest formula. It might look a little bit different to what you've seen before. Different places write different ways. This is the way that I like. Okay, A is the account balance, P is the principal, R is your interest rate, usually in your percentage per annum, okay? And sometimes you might see divide by 100 here. I like to convert it to a decimal immediately so you don't need to see that. Alright, but don't divide by 100 twice. If you have something like 6%, you don't want to do, like, you can do 6 over 100 or 0.06, alright, but not 0.06 out of 100. Okay, and I've seen this a few times in tests. That case, you've got a different number. All right, don't do that. And so T is rate. You've got a percentage per annum. Time is in years, and then N is your compounding periods per year. And so you'll notice how that changes your rate. And so R divided by N would end up giving you the percentage per period. So if this was monthly, you would divide by 12. If it was daily, you'd divide by 365. Okay? That said, you got to be careful because that's only when your rate is in a percentage per year. Okay? If it's already in a percentage per month, don't fiddle with it, except Tn, all right, the power will be the number of periods in total. Okay? So if T is in years and you've got this monthly, then 5 years times by 12 will give you 60 months, okay? You just need to understand that Rn is the percentage per period, okay, and Tn is the number of periods in total. All right? And if you pay attention to the details, it shouldn't be too much of a stretch, but usually this idea works, but that's because you usually get given a percentage per annum and you usually get given your time in years, but that's not always the case. So, compound interest is a geometric sequence. Recurrent relationship is in terms of n, but this time we're multiplying. You might recognize this part as the part of my interest rate. Okay, this is times together. N is a subscript here. Don't mix it up with this part here. All right, Tn plus 1 is equal to 1 plus R on N. This will give me the increase per period. Okay. Note that if you have, I might add this in a second. So if you've got yearly, N is 1, 6 monthly, N is 2, quarterly, N is 4, and then you usually get monthly, 12, weekly, fortnightly. Usually the ones that you're going to see people mix up on is the use yearly, 6 monthly, or quarterly. Okay, yearly because they're just focused on what this N is. All right. If you have yearly, then N is 1 and it just kind of disappears. All right, but a 6 monthly means you've got 2 periods per year. Quarterly means you've got 4. Quarterly is the one that usually messes people up because they think quarterly is every 3 months, so I'm going to use the number 3. All right, but then you're saying there's 3 periods per year, not 4, and you've got a problem. Anyways, so keep note of that. That might be useful to some of you. All right. So you have the increase in a period, and this will give you your following value. All right. Initial value, don't forget it. And how n is defined as matters beginning or end, different things. All right. Effective interest rate was poorly understood when we were looking at the test. Okay. Effective interest rate is usually best used when you're trying to compare different compound interest accounts. It doesn't quite work with your simple interest accounts, but it works very well with your compound interest. All right. So you've got one formula, or if you're using a TI, then you can use the EFF function. So, for example, EFF of 6% per annum for 12 months give me an effective interest rate of 6.17. All right, a bit more than 6 because you have it compounding every month in that situation. Yeah, we'll go through more examples when we actually get to it. With your finance solver, once we started to actually do a bit more complex problems and we had to have payments, the finance solver came in as your main tool, although you can use the lists and spreadsheets, but that's usually much better used when you're not going up to numbers like 200. Okay, 20, sure. 200, it's going to take a time. All right, finance solver is better in those situations. So you should all be familiar with how the finance solver is laid out, but just in case, you have the number of payments. Okay, this is going to be a focus a little bit later on because the final payment is going to differ a little bit. All right, the interest rate, this is per year, present value, payment, future value, payments per year, and compound periods per year. These last two, payments per year and compound periods per year, usually are the same number 99% of the time. Okay, but there's sometimes situations where you're going to be taking out payments regularly, but it might only be compounded quarterly, and I believe that's one example in the test. We'll get to that in some amount of minutes. All right, don't forget that your PV, PMT, and FV, your present value payment and future value, the sign has to change, and the easiest way to remember is that which way that money is going. If it's going from you to the bank, then you are technically losing that money for the time being. But if you've got an investment and you put in $5,000, then your present value would be minus 5,000. That money you have invested, it is away from you. Okay. If you're doing a loan, then the payments, as you're paying the bank back, it would be a negative value. Okay, but the present value, because you're getting that $10,000, say, to you initially, then it is a positive value for the present value, but negative payments. Okay, so each of the three types that we looked at of your annuities, repaying loans, receiving payments for an investment, and regular payments into an investment, changed what those positive or negative values were. So for your repaying loan, your present value was positive. Oops, try that again. But your payments were negative. Receiving payments for an investment, your payments were positive, but your I'm running out of room here. Present value was negative. Okay, because you've invested that money, you've initially lost it, but your payments coming back to you, so they're positive. Regular payments into investment, then your present value is negative. Okay, paid that to the bank, your payments are also negative. Some arrows would have helped here. Oh. And your future value, once you've finished paying into that loan for 5 years, 10 years, whatever, then your final balance is going to be positive. It's because you're getting that money back at the end of your investment. All right. Type 2, when you're receiving payments from an investment, has a situation that's called a perpetuity, and I'm pretty sure I've spelt it wrong here. No biggie. All right, I'm sure you'll fix that up later. But in the case of a perpetuity, it's where your interest in a period is equal to your payment. So if you have gained $500 for the month, then you only take out the $500 and you'll continue to get $500 every month for the foreseeable future. If you wanted to see something like that, so let's say we invest $5,000 and we get 4% per year. Okay, so it's going to increase by $200. If we only take out that $200, then no matter what we do, it will remain at $200. So you could have done 4% of $5,000, $200. So as long as you can work out a percentage of an amount, then you should be fine, okay? However, sometimes they throw it in that it's in monthly, so you might have to do what is the monthly payment and just divide it by 12. You can get $16 a month, okay? That's because, no, neither here nor there for now. Let's actually try the test. Alright, so hopefully this is beneficial to some. Alright, this is an old copy of the test, I believe, so there's a couple mistakes that I'll correct along the way. But Michael purchases office furniture valued at $3,700 on terms. Okay, on terms should be something that we recognized before. Look back at your textbook if you're unsure. Basically, that means that you have bought it on a situation where they are on terms. It kind of explains it in its name that you have some sort of requirement to pay it back, and sometimes they'll charge you extra if you don't. Anyways, valued at $3,700. So the item itself is $3,700. Anything that you pay later on top of this will be classified as interest. All right. We have a deposit of $370 and then 52 fortnightly installments of $71.56. How much interest does he pay in total? Okay, well, how much money does he pay in total is probably the first question that we want to ask. Okay, he pays $71.56 every fortnight, 52 times. He's also had to pay his deposit. Okay, that's an important part of his payments. He paid the $370, that's better, up front, and then he's had to pay 52 payments of $71.60 in order to own this office furniture of no description. 71.56 times 52 and 370. So he's had to pay $4,091.12. All right. From there, we need to figure out what the difference between the value of the item and how much he actually paid. Just remember that the interest is the amount above, and I said this earlier, interest can be thought of as the extra amount charged to borrow. Okay, he's taken the item, so technically he's borrowed the difference. Anyways, what would this be? To calculate a section, so might as well use it. And then we should have how much he's paid in interest. Now, you have to have that answer in order to get the correct answer for this next part. Calculate the annual flat rate. Okay, so we're looking at simple interest. I is equal to PRT. All right. Write your answer as a percentage correct to 2 decimal places. Okay, so we know that he's paid $391.12 in interest. All right. how much money did he actually borrow? Well, principal, forget that bracket there, is how much money he borrowed from this company. Now, he didn't borrow the full $3,700 because he paid a deposit. So we take that deposit away, and that's his principal. All right. The rate is what we're trying to find, and we have 52 fortnightly installments. Now, because we're trying to find an annual rate, it's going to be easier if we keep t to the number of years. All right. How many years is 52 fortnights? Well, there's 26 fortnights a year, so we've got 2 years. Okay. Now, if we just go to the solve function of our calculator, then we should get this. All right. Menu 3.1, solve 391.12. Now, what you're going to get when you type this in is, because we haven't divided this number r by 100, then you're going to get the decimal. If you wanted the percentage straight away, then you could add in that divide by 100 there. Okay, so we have r is equal to 5.87% per annum. Okay, so a couple tips. T annually, because we want an annual rate. Okay, if you used 52 in there, then you're going to get the fortnightly rate. You would need to multiply by 26. Okay, making sure that you can tie your interest to the next question. Okay, and then your principal was a bit tricky as well, because you have to actually figure out how much money he borrowed, which is the difference between the value of the item and the deposit. Okay, so there was a bit more in that question than you'd expect, but hopefully that makes a bit more sense now. Now, Narelle invests $87,000 in government bonds earning 6.25% per annum compounding daily. How much interest will she earn in 90 days? Okay, compounding, we should be thinking of the compound interest formula. All right, this is not a finance solver question because we don't have payments. However, if you kept payments to 0, then your finance solver would work it out anyway. But we're trying to figure out how much interest. All right. A is equal to P times by 1, add R on N, Tn. Which is equal to my principal is 87,000. 1 plus interest rate of 0.0625. Okay, as a decimal, 6.25%. Now, because this is daily, I'm going to have to change this per annum rate to daily. And I know that there's 90 days in total, so Tn, which I'd had before, is 90 in total. Now this would give me 27,000 times 1 add 0.025. Something doesn't. Oh, alright. We're fine. Sorry. 88351 is the account balance, the final account balance. Because we're trying to find out the interest, we would need to take away the principal, 37,000. Looks like I need to change my calculator to get me some extra decimal places. Okay. Document settings, float, do float 10. Alright, so had you been able to work out the amount or the and the final interest, then sorry, you would have also got 1 mark for your marking to make 3. What is the effective interest rate? On your TIs, this is a lot easier, but you can follow the formula, I imagine. E is equal to 1 add R on N. I'm pretty sure this isn't how it's written in your formula sheet, but I'm going to use this because it's far easier. We are doing 6.25% compounded daily, so it's 365 compound periods in a year, and then we get 6.45% per annum. Clearly that's not the entire answer, but I've just rounded to 2 decimal places here. Okay. Jerry takes out a loan for $32,000, agreeing to repay $600 at the end of each monthly period, with a compound interest of 8% per annum, compounded monthly. This is per annum, so we might need to do something with that. Write a recurrent relationship to represent the value remaining in this account at the beginning of the nth month. The beginning of the nth month. Alright, so got to be careful there as well. Write a recurrent relationship, which means we're doing Tm plus 1. What is happening from month to month in this case? Okay, because n is in months. Well, it is increasing by 8% per year, but it is compounded monthly, so it is increasing by 1/12 of 8%. So, but we also have this payment, okay? Because it's a loan, the loan would increase a little, his payment would be reducing it a little. And at the beginning of the first month, T1, it is $32,000. Okay, probably could have been worth more marks here, to be honest, but you would have got 1 mark for the initial value and 1 mark for the actual recurrent relationship itself. Okay, I'm not too fussed about you working out what this actually is, but just in case, 1 add 12%. It might also look like that. Okay, how much will he still owe in this loan, on this loan after 3 years? Now we could do this a few different ways, but I think the list and spreadsheets way would probably be easiest. At the beginning of the first year, it is $32,000. Alright, and you got to be careful here because what we're actually going to be looking for is after 3 years. So we're actually looking at the beginning of the 37th month. Alright. Finance solver actually I'll go over in a second. So A1 times by 1 plus 12.8%, take your 600, okay, and take it down to 37. You might have a better way of doing this than what I've got. Alright, and it looks like we've got 16,326.25. We should get the same number if I did this via the finance solver menu. One. Okay. How much will we still owe after 3 years? 36 months. Okay. Interest rate of 8%, present value of 32,000. Okay, but it is a loan. Just making sure we get the positive and negatives right here. Loan of $32,000. Okay, means it's positive to begin with. His payments would be negative. Future value, that's what we're trying to work out. Payments per year, 12 months a year, and it's compounded monthly as well. So 16,326.25, which is exactly what we had. Cool, moving on. How long would it take him to pay off his loan? This is more of a finance solver question. Okay, how long? We want his future value to be 0. By the way, it's one of the difficulties that we get when marking these kinds of problems is that because you're using the finance solver so much, we have difficulty knowing how you've used it. So showing what numbers you have typed in for each part of your finance solver gives us some idea of where your head's at. If you just write the number, then with no justification, we can only assume you've done it wrong the entire way. All right, if you get the wrong number. Future value is 0. How long? Whoops. I'm trying to figure out how long, how many payments would be another way to think about that. So it would be 66 and a bit payments, which means it's going to take 67 months. All right. 67 months with a smaller final payment. What would his final payment be? This tends to cause a bit of issues. Okay. Notice how here we've got 66.12 payments. We need to figure out how much he's going to pay in total. Okay, let me drag this down to 68 in this case. Okay, so you'll notice that at the beginning of his 67th month, he hasn't actually paid it off. So after the 67th month, at the beginning of the 68th, okay, then he would, and we want to figure out what his final payment would be. Well, he needs to pay whatever the 67th month value was plus the interest. So if we remove this payment like I've just done, okay, if we remove the payment, then it will show us how much he needs to pay in order to reduce it to 0. So if we take that 74.88, then it's reduced it close enough to 0 on his after 67 months. So we've got $74.88. How do we do this on the finance solver? Would be a valid question. That's what I hear people ask. Well, a couple ways to think about it. How much has he overpaid after 67 months? Okay, he's overpaid by $525.12. Okay, if we find the difference between his payment and the $525.112, then you would get the $74.88, which is what we got there. So try to use the finance solver to your benefit. Okay, see how much is overpaid, and then find the difference to figure out how much that final payment should have been rather than the $600. How much interest has Michael paid? Well, in this case, Michael has paid $600. Back here. $600 66 times, and then $74.88 on his final month. Sorry, I haven't quite read the question properly. That's how much is paid in total. The interest, however, okay, is the difference between how much his loan, or how much money he borrowed, and how much money he paid. So if we do the $39,674.88 that he paid, and we take away his loan amount, then we get the amount here. Okay, just double check that number is correct because I was reading it off my previous set of solutions. 7674.88. Okay, so being able to figure out how much is paid in total, as well as the interest, recognizing that how much is paid is not the interest, is good. Suppose instead that Jerry made monthly payments of $750. How much money would Jerry save? Okay. Basically, we're going to have to repeat these steps that we've done for the past few questions. Okay. I prefer this finance solver, so we want to know how long it's going to take him to pay it off. Hold on a second. Negative payments, John. There we go. So 51 months it's going to take him to pay this off. At that 51st month, how much has he overpaid? So we're going to do the difference between how much he should have, or how much he is paying a month, and how much he has overpaid. There are other ways to do this, but I'll try not to go over to them, otherwise usually serves to confuse people. Okay, so we know that he paid this on his final month. Alright, so how much has he paid in total would probably be a good question. Alright, he's paid 50 lots of 750 plus 279.26. Now, the difference between how much he's paid in this situation and how much is paid in the prior situation, the difference between those two will be how much he saved. So we're going to do 39674.88 take your 3779.26. Alright, so he saved $1,895.62. Okay, so notice that it was just a repeat of the prior steps that we did. How long, final repayment, how much is he paid is part of part E, and then we can find the difference between the two for that third mark. Alright, Upon retirement, Wesley switches his superannuation fund of $480,000 into an investment account, paying 9% per annum compounded monthly. Wesley wants 4 payments per year for as long as possible. So notice how the compounding periods, compounded monthly and 4 payments per year, are different. This is one of those situations that I mentioned before where your compounding periods per year, 12, this means your CPY is equal to 12, and your payments per year actually differ. Alright, bit of a tricky situation, but it's basically paying attention to how you use your finance solver rather than just assuming that they're always going to be the same. How many payments of $15,000 will this scheme allow Wesley to receive? How many payments of $15,000? So in our previous problem, we noticed that his payments, we've got 67 months, but a smaller final payment. This will be similar for Wesley. His final payment will be smaller than $15,000, so we're not actually going to include that. All right, how many payments of $15,000? Finance solver. All right, N, I, PV, PMT, and FV, and we already know our CPY and PPY. And how many payments? That's the part we're trying to find. Interest 9% per year. Present value is an investment of $480,000. His payments, we know, are coming to him, positive $15,000, and his future value will be 0. To make this quick, I am running out of battery. 9 minus 480,000. PPY, there is 4 payments per year of $15,000, but his compounded period per year is 12, because it's compounded monthly. And so we have N is 57.66. So this means that he's going to have 57 full payments of $15,000. So 57 payments would be our actual answer here. How many payments of $15,000? 57, because that last one, his 58th, would not be a complete $15,000. How many years will it last? Okay, well, there's 57 payments and it is done quarterly, so maybe I thought about this wrong. How many years will it last? We could think about it as 58. Yeah. Same idea. Regardless, we want to know how many, if there's 57 payments of the full $15,000, then it would be 14.25 years. Okay. If you wanted to consider that last payment still a part of his superannuation, which is perfectly valid, then you could think about it as his payment scheme would actually last 14.5 years, but that last payment would be slightly smaller. Okay, I was personally looking for the 14.25, but as long as you're dividing this payment, the number of payments, by 4, you should get the similar answer. What would be the final payment that Wesley receives that closes the account? Well, let's go back to the finance solver. How much would he have overpaid? Okay. Yeah, that would work. 15,000 take 5075.77. 9,924.23. If you wanted to, you could think about it in a list and spreadsheets situation. Alright, you start with, that's going to get complicated because the compounded periods monthly doesn't match with the payments per year, and you'd have to start using effective interest rates, and it's not something that we're going to go through here. Anyways, that should be enough. His final payment is slightly smaller. Notice that it's about 2/3 of a full payment, which makes it about $10,000. Yeah, 2/3 of $15,000. Olivia wishes to invest $10,000 and is considering a 4-year or 7-year investment. She has narrowed her options down to the following 3 accounts: flat rate of 9%, compound interest at 7.25, and compound interest at 7.5. B is compounded weekly, C is compounded annually. We can compare B and C quite easily using our effective interest rate. So the effective interest rate of B would be 7.25%, and it is compounded weekly. So B is actually making 7.51% per annum, which is better than account C. So account C's effective interest rate is always going to be 7.5% because it is annually anyway. Account B will always be better than C. Now we've eliminated C as an option. We just need to compare A and B. Okay, so let's look at A and B at a 4-year investment and a 7-year investment. Do not need to think about C in this case because we've already eliminated it. So with A as your flat rate, okay, they're making 9% every year. So after 4 years, it's going to add on 3,600, and after 7 years, try that again, it would add on 6,300. Flat rate interest is fairly simple, so you could use your I is equal to PRT and add it on to your principal and you get those numbers. Alright, your account B compound interest, alright, we've got $10,000 times by 1 add 0.0725, compounded weekly for 4 years. So how many weeks are there in 4 years? There is 4 times 52. Okay, and we get 13,361.58. And if we take the same situation, battery's really getting flat. Go to 7 years instead, 1605.46. And now let's take a look. What's happening here? We've got A is bigger than B for the 4-year investment, but smaller than B for the 7 years. So for Olivia here, if 4 years, we want to go account A. If 7 years, account B. Okay, so your 4 marks would have come from using your effective interest rate to show that account B is always better than account C. Compare those compound interest accounts, which is where your effective interest rate really shines. All right, you're working out and then your justification here. got? Should be okay for a little bit longer. An investor purchased a set of old coins for 12,900, expecting the value of this set to increase by 5.5% each year. A current relation that can be used to model the value Vn of the set of coins n years after. Okay, this is after they were bought. Remember, beginning, end, that changes. Go back to the beginning of the video if you're unsure about that. They were bought is Vn plus 1 is equal to Vn times R, and V0, so after 0 years, is equal to A. State the values of R and A. Well, 5.5% per year, and we're doing N in years, so this should be 1.055 because it is increasing and we want to find the value, not the interest. Okay, A would be equal to the value after 0 years, which means nothing has happened, so $12,900. And that should be your 2 marks there. Use the relation to calculate the expected value of the set of coins after 5 years, giving your answer to the nearest $100. People tend to miss this detail here. Giving your answer to the nearest $100, that's actually worth a mark in and of itself. Any answer that you give, assuming you rounded it to $100, would get you that mark. Alright. Use the relation to calculate the expected value of the set of coins after 5 years. Well, we could look at this in a few different ways, but we'll probably just go to our list and spreadsheets. Okay. After 1 year, okay, I'm going to use the numbers on the left-hand side here. After 1 year, it has increased by 1.05, 5.5%. Okay, and then A1 has increased by the same percentage. And we want to look at after 5 years. So 16,859.78, but we want to go to the nearest $100. So what would that look like to us? 16,900. Alright. So it's 1 mark for the actual solution, but 1 mark for following the instructions of the question. How many years will it take for the value of the coin to double? Alright. Probably a few different ways to look at this, but if we're looking at the compound interest formula, it's got a double. What is double of 12,900? 25800 is equal to 12,900 times by 1 add 0.055. We want to know how many years it's taking to do it. You could plausibly do this on your list and spreadsheets and you find where 25,800 is happening. Okay, so after 12 years, not enough. After 13 years is looking pretty good. Okay. If you were to solve the problem that we've this equation here, comma n, 12.95, rounding up to the nearest year, 13 years. Cool. The investor could have left 12,900 in savings account, paying 5.3% per annum, compounded monthly. Determine the effective annual interest rate. Okay, so EFF of 5.3 compounded monthly is 12. 5.43% per annum. Okay, if we're comparing 5.43% per annum to the 5.5% per annum that we get for the coins, which one's better? And clearly the coins are better. Spencer borrows $300,000. This is a long-winded one, and due to the fact that I have low battery, I will come back and see if I can finish question 7 afterwards. Okay. An annuity is set up with an initial sum of $200,000 and guaranteed an interest rate of 4.2% per annum compounded monthly. Guaranteed's nice. If a regular monthly payment of $950 are withdrawn at the end of each month, just after the interest is added, balance of the annuity AN after N withdrawals will be given by the recurrence relation AN plus 1 is equal to 1.0035 times by so on and so forth. Explain the relevance of the figure 1.0035 in the relationship and state the value of D. Well, let's start with the easy part. Value of D, we are taking $950 every month. Okay, the 1.0035 is the increase per month, which comes from the 4.2%, 0.042 divided by 12. Just to demonstrate for 0.042 divided by 12. Alright, determine the maximum monthly withdrawal that can be made if the annuity is to last for exactly 12 years. So, and 12 years is 12 times 12. I is still 4.2%. Present value is annuity is set up. So this is an investment, is initially losing the $200,000, but is getting it back slowly in positive payments. Compounded monthly is taking out payments monthly, so they're both 12 as well. Sorry, maximum monthly, oh, my bad. Determine the maximum monthly withdrawal. We actually want to know what the payments are. So they're not $950 in part B. We want to work that out. $144 months, 4.2 payments. That's what we're working out. Come back to it. Whoops. That's better. Alright. Yeah. Well, he's got payments of $1770.54 every month for 12 years. It's not bad. If we want to make it last forever, alright, then we need the interest to match the payments. So how much interest is he making in this 1 month? Well, we actually worked that out in part A. It's 1.0035 times by the 200,000. Alright, well, better yet, just the 0.035. But we should be able to see the number anyway. Should be able to make $700 from that every month forever. Okay, part C was a mistake. The intention of that question was supposed to be, what interest rate do you need in order to get payments of $1,050 but we wanted that to be a perpetuity as well, which wasn't clearly stated. My bad. Theo is saving in order to take an extended break from work. They open a new account and intend to invest. So a new account is important information. Invest $800 a month for 3 years, compounded monthly, 3.5% per annum. All right. If they kept their money in the account but compounded weekly, how long can their break be? So that was another mistake. How long can their break be if they needed full payments of $450 a week? Full payments. All right. So we're going to have to break this up into 2 parts. We've got the time that Theo is saving. PV, PNT, FV, PPY. So in this part of Theo's question here, they open a new account, which means the present value is 0. They are investing $800 a month, okay, and it is also compounded monthly at 3.5% per annum, okay, and this is for 3 years, 3 lots of 12. We want to know how much money Theo has at the end of those 3 years. And it's over. Love this thing. Does all the hard work for you. So, we know that Theo has saved $30,319.78. Uh-oh. Now, if Theo is keeping this money in this account, then this is her present value. So she reinvests that, but it is compounded weekly, and she has payments that are weekly of $450. How long will this last? How many full payments? Okay, so we have n is equal to, that's what we're trying to figure out, 3.5%, present value, negative 30319.78, payments, positive $450, future value going back down to 0. And so n was equal to 68.97, which means there's 68.97 payments in there, but we want to know how many full payments there are, which means 68 payments. Now, if you just divided that value by your $450, then you're not accounting for the fact that you've got it in a compound interest account. You just got it in cash and you're taking $450 each day or each week. Anyways, sorry about not being able to get question 7 done. I'll see if I can make that a separate recording another time, but basically this one's going to be a repeat of what we did in question 3 a couple times for both styles of accounts, where you have to figure out your final payments and then figure out the difference between the months, because you want to know how much time he can save, and the difference between how much he spends in both situations. Let me know how you go with it. If you do need that one to go through again, answers are on Connect or around the place, I'm sure. And then, yeah, let me know if you have any problems. I hope that's helped. We will see you next time.